Alright, what's up everybody? How are we doing? Happy Wednesday, happy hump day. Hello. How goes it everybody? Happy Wednesday. It's on orbit, I just have to assemble the solar panels. What, you sent them up not assembled? Do you have KAS or KIS? How do you plan on assembling them in orbit? Or are you saying the solar panels are attached to some component and you just need to rearrange them? I don't know. Good. Good is good. Good is always good. I'm doing alright too. Get ready. That. Which are the two things that I said? Lots of math today. Lots of awesome math. It should be fun. It should be a lot of fun. We're going over what's called the orbit equation. And what the orbit equation, it's quite literally called the orbit equation. And what this equation will allow us to do is, find our sixth element, our element that depends on time, which is the last element we need. Attached but not assembled. Wait, so I was, sorry, Mech, I was asking, did you send them up in, like, an inventory? Like, KIS? Do you have KIS and you're just gonna slap them on the side? Or, wait, attached but not assembled. Oh, okay, never mind. So you're saying they're already attached on the side, and you're just going to move the different components around until they look right. Okay, I got it. Your game save must be pretty wild, Mank. That must be a pretty wild game save. The element of surprise. This will be the element of surprise for a reason. I'm not going to tell you what reason quite yet, but in the process of deriving the sixth element, we actually rederive another element in a different way. And you're gonna see it, and you're gonna be like, what? I didn't expect that! That's awesome! And you're gonna say, I love math! Here's what we're doing. It's just 2 pages. We've got this, and we've got this. That's it, right there. 2 pages. That, and that. We're gonna get through this stuff today. And again, I just re-derived this before I started the stream. I don't know if you guys can see that or not. Probably can't even see it, quality-wise. I'd be impressed if you can. Let me test, now that I'm watching the stream. I'm curious if you guys can see the writing on this. It's probably a bit blurry, right? Oh, never mind, you can see the writing fine. It's just backwards, obviously. Oh boy, but anyway, that's what we're doing. It definitely does depend on timing. It does depend on timing. Well, good surprises. You can also have bad surprises that don't necessarily depend on timing. Right? A bad surprise can happen regardless of what time it is. And we're gonna... Well, let's see. I'm gonna review a few things to start. And then I'm gonna go right into the derivation. We're gonna power through this. Because, again, all of this boils down to one equation that's like half an inch long on the paper. And once we get there, then I will show you how to use the equation. And then we're going to look over the worksheet, which is already up on the Discord and on the Google Drive. But I'll go over the worksheet on the stream so you guys have an idea as to what I mean from some of these questions. Like the thunderbolts and lightning. That was horrifying. That was still, by far, one of the most horrifying things I've ever experienced. Not a fan. Not a fan of that ever happening to me again. I hope it doesn't. Sound-wise, how are we doing sound-wise? I hope the music isn't too loud. I don't think it's too loud. I think we're fine sound-wise. Okay, well, hopefully. If not, then, oh well. I hope it happens to me. You don't hope it happens to you. You're wrong. Dude, it was... I can't stress it enough how unexpected it was. And you have no idea. I mean, it was already dark outside, and my eyes were obviously adjusted to these spotlights shining in my face. So when everything turned off, pure darkness. Instantaneous pure darkness. Hey, Kerbonaut, what's up, man? Sound is good? Alright, that's good to know. Good is good. Sound's always good. Good sound is good. That's good. Well, I guess we could probably just get to work because we've got plenty of stuff to derive. Yeah, sorry about the confusion timing-wise. I'd set up a Skype call with AYE. We were going to Skype at a certain point, and I miscalculated. I miscalculated by a whole hour. I was like, oh, wait, never mind. I have to do this. But I ended up just shifting this back an hour anyway, and we're all fine now. So let's just get to work. I gotta stop delaying this. I'm trying to savor the moments before I get into this derivation. But let's start. No more fooling around. I'm gonna take my headphones out because it's not like you guys are talking to me. You guys are just chatting, so I don't need to listen to you. Alright, so let's go into here. Alright, the sixth element. Oh boy. And this is technically lesson 4? Yes. Lesson 004. I'm just gonna leave that there. And I could probably do with a slightly smaller size pen. So anyway. Oh boy. What we already know is this. What we already know are these 5 elements that we typically use. These aren't the only 5 elements that you can use, but they're common to use. They're not always the best choice for elements, but it just happens to be that in most cases, in most orbits, this set of elements is fine to use. We've got semi-major axis, eccentricity, inclination, right ascension of the ascending node, and argument of periapsis. Not dependent on time. Dependent on time. So what we need, we now need a time-dependent variable, a time-dependent element that will allow us to determine where we are along the orbit. That's just as important as any of these other parameters. Now we need a time-dependent element. Yeah, because again, at this point, we've got everything defined for our orbit. We've got a nice little planet there. Let's call that the Earth. And we've got our orbit with the planet at one of the foci of the ellipse. Right? But we don't know where we are along the orbit. That's the problem. Yeah, we have no idea where we are along the orbit, unfortunately. Oh, come on, you fool. Who knew arrows would be so difficult? We have no idea where we are along the orbit. So obviously, you know, first looking at this, you'd think, okay, we'd probably want an angle. An angle would probably be the best way to approach this, and you bet it is. We're gonna start with the good old this isn't a okay. I'm gonna start with this. I'm gonna say time dependent because it's really not time dependent. It's, I guess a better way to put it is trail, path dependent, right? Path dependent. Because this derivation, wow, good spelling on dependent there. What this actually will be is an equation that starts with a component that's with respect to time, and we're going to get rid of that component. Dependent. I'm gonna fit that in there. Okay, cool. Good enough. That looks like crap, doesn't it? Let me just move these over here. Still getting used to this pen. I'm not perfect at using it yet. Come on. Alright, we need a time-dependent element. But what I really mean is path-dependent, right? We want something that allows us to see where we are along the orbit. And this specific derivation will actually not depend on time. The one that depends on time is way more complex than this. And I might just give you the equation for that, but we'll see what happens. We're going to start with the following equation. Good old Newton's law of gravitation, which you guys have come to know and love by now, hopefully. We've surely used it enough. Are you going to page down for me? There we go. So we're going to start with this. Oh. Well, first, yeah, maybe I should go over these. I'm going to go over all of the assumptions and theories that we're going to have to make. Assumptions and theories and theorems. Alright? First things first, a little bit of vector work, right? The magnitude of our vector will go like this. Kelly, what's up? Is just that, right? That's just the magnitude of r. The magnitude... Well, I should probably start with something else, shouldn't I? Ugh, assumptions. I know, but we have to make them. R dot, R with a little dot on top of it, is actually just the derivative of the r vector with respect to time, which is also v, right? Like that. And, not to mention, the magnitude of r dot is just r dot, and that's just v, okay? And then lastly, r double dot, when you see two r's at the top, it's the time derivative of r dot with respect to time, or the time derivative of velocity, which is acceleration. And, as always, to get the magnitude of the acceleration, we're just going to write it like this. Okay, so those are all the things that we have to know. It's relatively straightforward to follow. It's the dot notation. You'll hear me say things throughout this procedure. I guess you could call it a procedure. It's a nasty procedure. Like r dot, r double dot. R dot just means velocity, and r double dot will mean acceleration. That's all you have to remember, okay? The other few things that you need to keep in mind. The dot product of one vector to itself is equal to the magnitude of itself multiplied by the magnitude of itself, which is equal to the magnitude squared. Pretty straightforward, okay? Another thing that we can assume, the vector dot product, well, if you take the dot product of a vector with the time derivative of that vector, that's equal to the magnitude of the vector multiplied by the magnitude of the time derivative. Okay, that's another thing you have to keep in mind. What else do you have to keep in mind? You have to keep in mind a lot. Okay, so assumptions and theorems. So these are all things you have to keep in mind right here. And then the other thing, you didn't, why, I don't know why you didn't get a notification. You might have notifications turned off. I don't know. Anyway, the other thing you're going to allow is three, what I'm going to call, what did I call them in the notes? 3 pointless moves, okay? You will allow me 3 pointless moves, okay? And the reason these moves are pointless, well, you'll see why. They're, no, Kelly. No. Whoa, here it is. Allow me 3 pointless moves to make. And when I say pointless, I essentially mean I am going to do something mathematically that has absolutely no reason why I should be doing it, but I'm going to do it anyway because it's correct to do mathematically and I'm allowed to do it and you can't stop me. The whole thing is that there are points in this derivation where mathematicians like Laplace and Euler, better luck next time, Kelly. You gotta catch me more off guard. People like Laplace and mathematicians, brilliant mathematicians like Laplace and Euler had made these pointless moves to get to the point where we are today. And you will not be able to find anywhere online any reasoning behind this move. It doesn't make any physical sense. It has absolutely no physical mathematical sense, but it's entirely pointless. And you're going to allow 3 of those tonight. You're going to allow 3 of them, and I will point them out when they arrive. Okay? Alright, who's ready? You guys ready? I'm ready. It's going to be fun. Alright, so you're allowing me 3 pointless moves. You're going to have to keep in mind all this stuff. The magnitude, right? If I want to do the magnitude of the vector, all I have to do is draw the symbol that represents the vector without the arrow, and then it's exactly the same at that point. You see, I do that here, I do that here, and I do that here. Was he really? I did not know that. I didn't even know that he was from the States. I thought he was overseas. I could have sworn that he was overseas. Are you pulling my leg? Alright, so we're going to start with good old gravity, right? So let's go like this. R vector double dot. So the acceleration any body will feel if that body is in a 2-body system. Okay, you can stop now. Oh, Kelly. I knew something was up with the kappa. I was like, what is he doing here? R double dot, the acceleration felt is equal to the gravitational parameter. Hey, give me some slack here. Over the magnitude of your radius cubed multiplied by, oh, well, I need a negative sign here. So let's throw in a negative. What shall we throw in a negative, right? Because acceleration occurs inwards. It doesn't occur outwards. It's a negative gravitational parameter over your radius magnitude cubed multiplied by your position vector. And sorry, this isn't radius, it's position technically. It's position. Position vector, okay? So your acceleration is in some way related to your acceleration. Your acceleration is in some way related to your position. We're going to start with this. And we also already know angular momentum, right, is equal to your position vector crossed with your velocity vector. And with this new notation, that's equal to position vector crossed with r dot. So it's r crossed with r dot, right? The first thing we're going to do is this. We are going to take the derivative of this. So right here, take the derivative of all of it with respect to time. Euler is Swiss. Okay, well, I trust Google. I didn't think he was American. So let's do that, right? So the derivative of the angular momentum vector with respect to time, and I'm gonna cut this off here because that's not part of the derivation. The derivative of the angular momentum vector with respect to time, and for those of you guys that have taken calculus, you should know that if you have 2 terms like this, it's the first term multiplied by the derivative of the second plus the second multiplied by the derivative of the first. That's all it is, okay? And let's take a look at this. The change, so what does this represent, right? It represents if the angular momentum vector is changing at all. That's all it's representing. dH over dt is equal to, then this, the derivative with respect to time of r crossed with r dot, right? R cross v, that's what it is, which is equal to r crossed with r double dot plus, which is 1 derivative of 2 plus 2 derivative of 1, which is r dot. As you guys probably know, a vector, well, if you don't know, then new knowledge for you. A vector crossed with itself, that's actually just 0. And it's a 0 vector. It's not a scalar term. It's a 0 vector, but it's 0, okay? And check this out. We actually already know what r double dot is, too. So, because of the equation above, r crossed with negative mu over r cubed r. Right, so this is then equal to negative mu over r cubed r cross r. Wow, look at that. Another one of these, which is also equal to the 0 vector. So what does that mean? Well, that means, oh, different color for different meaning. The derivative of the angular momentum vector with respect to time is 0, okay? Angular momentum does not change in the two-body problem, which makes sense, right? If you've got a two-body problem, then your orbit stays the same. Your orbit doesn't rotate all over the place, right? Your orbit stays the same. That's what this says. Angular momentum is constant. That's what that says right there. Okay. So that was the easy part. Now let's get into the tough part. We've got this equation right here. Is this AERO 101? Yeah, this is AERO 101, man. We are deriving the orbit equation. It's an equation that's quite literally called the orbit equation. So, we've got the derivative of the angular momentum with respect to time is 0, which would make sense, right? If you've got an orbit, dang, wrong class, get out of here. If you've got an orbit, your orbit doesn't, continuously change orientation over time. In the two-body problem, right? In the two-body mass point problem, your orbit will constantly stay the same, and that's what this derivation says right here. But let's continue onward. So let's go back to here, and it's like this. All right. So r double dot is equal to a negative mu over r cubed multiplied by your position vector. Okay? You guys ready for pointless move number 1? No imagination? I know, man. The orbit equation? How unoriginal. Pointless move number 1. You guys are allowing me 3 pointless moves tonight, okay? We're gonna cross everything. We're gonna cross quite literally everything with the angular momentum vector. We're gonna take this whole equation and we're gonna cross it with the angular momentum vector. Why? It's a pointless move, don't worry about it. But it's required. If Euler says it's required, then it's required, okay? So, that means we have this, right? Our acceleration double dot crossed with the angular momentum, well, not acceleration double dot, it's r double dot, and again, this notation is 2 time derivatives of the position vector, right? And you've got position, velocity, acceleration, so that's acceleration. Crossed with angular momentum vector is equal to negative mu over r cubed, r cross h. We're just crossing the whole thing with h. Why? Don't worry about it. We are going to denote, yada yada yada. How do I want to denote this? Probably would want to denote it with a new color and a new thickness, huh? New color. Okay, cool. Who's this Euler guy? It's E-U-L-E-R. It's Euler. And it's not pronounced Euler, it's Euler. It's pronounced Euler. It's E-U-L-E-R. Phonetically, it's Euler. Anyway, we've got this, which is the right-hand side of the equation. Oh boy, did I just do that live on stream? This is the left-hand side of the equation, and this is the right-hand side of the equation. You saw nothing. You saw nothing. And this is the right-hand side of the equation. Of course I know that. Of course I know that, okay? What's up, Threnan? How are you? So, left hand and right hand. Kelly, that joke. Left-hand side and right-hand side. We're going to do some modifications with the left-hand side and the right-hand side, and we're going to see if we can make this a little bit simpler to understand, right? First thing we're going to do is well, you'll see. Alright, so here's how I like to think about this, right? This is at a different level than the other objects, right? You're taking 2 time derivatives of this, but there's no derivative here. There's no derivative here, there's no derivative here, but there's a derivative here, okay? So we have terms that are on different levels, derivation-wise. So we want everything on the same level. We want everything on the same level, right? Level playing field, that's what we're all about here. So same level. So we want everything on the same level. We've got some things that are time derivatives of the vectors, and then we've got regular vectors. We don't want that. We just want everything to be level. And the way to do that is really weird. But we're going to do it anyway. So, note this. Let's start with the left-hand side here, right? So let's go, we're actually going to make this a different color than the right-hand side. So, left hand. Cool. Left-hand side. Hey, you knew something, Kelly. No, you're smart. Get out of here. Anyway, we're going to start with the left-hand side, okay? So we're going to note the following. I don't know how they figured this stuff out, but it's really cool. Note the following, okay? The time derivative, the derivative with respect to time of r dot, so velocity crossed with angular momentum, is equal to, remember, it's 1 derivative of 2 plus 2 derivative of 1, or 2 crossed with derivative of 1. Hey, Kyran, what's up, man? So let's take a look at what this is, right? So, it's 1 derivative crossed with the derivative of the second term plus the second term crossed with the derivative of the first. Well, that's actually the wrong notation. Sorry. You have to keep the order here when you're crossing. Plus the first derivative crossed with the second term. Okay? Do you guys notice anything? This right here, right, is the same as this right here. So if we move this over to this side, we can actually come up with an equation. So we've got this then. We know that the acceleration vector crossed with the angular momentum vector is equal to the time derivative of the velocity vector crossed with the angular momentum vector minus the velocity vector crossed with the angular momentum vector. Okay? Pretty straightforward, right? But we also know one thing, right? Check this out. Oh, sorry. This is a dot right here. Yeah, because this is a dot. Guys, check this out. We've got this fancy term here. I'm going to see if you guys know this. You guys should know this, right? Because we just did this. We've got an h vector dot. The time derivative of the angular momentum vector. This represents the change of the angular momentum vector. What did we just derive about the angular momentum vector, about the angular momentum vector changing? What did we just derive about that? And while you guys figure that out, I'm going to continue onward, so hopefully you guys can figure that out. Whoa. Yeah, Kelly, you got it, man. This right here is actually just 0. So, we've got this then. The acceleration vector, so therefore, the acceleration vector crossed with the angular momentum vector, which is on the left-hand side of the equation, is equal to d over dt, the time derivative of the velocity vector crossed with the angular momentum vector. Okay? Now, again, we're trying to put everything on the same playing field here, right? We've got something that has a double time derivative of a vector, and then we've got things that aren't vectors at all, okay? I'm just going to keep reminding you guys that because that's the end goal here. We've got something that has a double derivative of a vector, and we've got other things that aren't at all. So if we get everything into double derivatives, that's awesome. If we get everything into single derivatives, that's awesome. But we need to put everything on the same playing field. That's what we're trying to do here. So, or scalars, yeah. I mean, I'm even talking about just vector notation too. But I don't want any derivatives unless everything is a derivative on the same level. Okay. Hey YOLO, what's up, man? How are you? So we've got this now, right? So we've got all Oilers on the same field. You got it, Kelly. So we've got this, which is equal to the left-hand side, right? This right here, that's equal to LH. That's equal to the left-hand side of this nasty equation that we came up with when we made the pointless move to cross gravity with the angular momentum vector. Again, I don't know how these guys figured it out, but it's awesome. It's awesome, and it's a lot of fun to derive. So, we've got this, all right? And we're going to leave this as is for now, and we're going to work on the right-hand side now. So, LH right here. Now we're going to work on the right-hand side. And the right-hand side is right here. Yeah, I know. Euler. Yeah, well, it's Euler. It's Euler. It's Euler. It's Euler. It's pronounced Euler. That's how I learned it. A lot of people say Euler, so you'll hear, you know, Euler angles. But everybody that I work with, and through my academia, I was taught Euler. It's pronounced Euler angles. But, you know, whatever. It all depends. It's a name, alright? I'm sure he pronounced it both ways, right? All right, so we're going to look at the right-hand side, right? The right-hand side is this. The time derivative of the velocity vector crossed with angular momentum. Guys, just hang on, okay? Yep, f prime. That's what we're doing, YOLO. We're taking derivatives. That's exactly what we're doing. Anything that you see a dot above it, YOLO, anything that you see a dot above it is just the derivative. Anyway, so we've got this as the right-hand side, right? Let's take a look at something, right? Oh, wait, that's not the right-hand side at all. Sorry. Let's go back and look at the equation real quick, just so I don't muck up. This is the right-hand side, okay? This is the right-hand side. We're going to be doing the majority of our work with this component of the right, because mu is just a constant. Who cares about constants? We can do anything we want with constants later, but we're looking at this component right here, okay? So, let's take a look. Subprimes, it sounds like 2008. You get. What's the first derivative test? What do you mean? There's multiple first derivative tests. Which one are you talking about, YOLO? So anyway, we're going to look at just that component, which is this. 1 over the magnitude of your position vector cubed multiplied by the cross product of your position vector and your angular momentum vector. But we know angular momentum vector, we know that, right, is equal to 1 over r cubed multiplied by the quantity of your position vector crossed with, what is angular momentum? It's just your position crossed with your velocity. That's all angular momentum is, okay? That's all it is. And we're going to use a nice little vector theorem. That looks like this, okay? Vector A crossed with the quantity of vector B crossed with vector C is equal to the vector B multiplied by the scalar dot product of vector A and vector C minus the vector C multiplied by the scalar dot product of vector A and vector B. How people came up with this, don't ask. We don't need to worry about that, YOLO. But yeah, that is a check that you can do, YOLO Swaggins. That is a check that you can do, absolutely. No, it will not, Kyran. How did people come up with this? Beats me. But that is a true theorem about vectors. So, there you go. So we're going to use this we're going to use proof it didn't happen, whatever. I might change that value to 4, but whatever. I'm allowed... Well, yeah, this doesn't count, because I'm going to assume this is a theorem. You're allowing me 3 pointless moves tonight, Kyran. 3 pointless moves. We've already made 1 pointless move. We literally just took the gravitational equation, Newton's law of gravitation, and crossed it with angular momentum. Doesn't have any physical significance at all, but we did it. So that's my first pointless move. We're going to make another one a little bit later. So we have this vector theorem. So we've got an r cross quantity r cross r dot. So let's apply this, right? So this is then, right, A, this is B, and this is C. So let's take a look then. We know then r crossed with the quantity of vector r crossed with the vector r dot is equal to r quantity multiplied by the quantity of the dot product of r dotted with r dot minus r dot vector multiplied by the quantity of the dot product of r dot r. I told you guys to just hang in there, okay? I told you guys to hang in there. Tis true, man, tis true. But check this out. We also know that r dot r is just equal to r squared. And we also know that r dot is equal to r dot. That sentence sounded ridiculous when I said it. Anyway, so we now know this, right? 1 over r cubed r cross h is then equal to the following, right? It's equal to 1 over r cubed r, right here. Whoa, that's not really an arrow. Multiplied by r dot minus r dot vector r squared. And check this out. We can actually remove, this goes down to a 2, this goes away, and this goes down to a 1. So this is now equal to just this. r vector multiplied by r dot minus r dot vector multiplied by r over r squared. You guys are gonna love this. Beautiful, YOLO. We're allowing Chiren to... All of these R's call for some serious R. Yeah, I agree, man. So, anyway, nice, Novus. I'll take a look at that in just a second, man. Well, I think I have to open it just to save it anyway, but... Okay, got it. These are not the equations you're looking for. I like it. Anyway, so, for those of you guys that have... That's not right. For those of you guys that have taken calculus before, you know that the derivative of a quotient is low d high minus high d low over denominator squared. Well, check this fancy thing out. We know the time derivative of vector r over r is equal to the following. Low times the derivative of high minus high times the derivative of low over denominator squared. Does that look familiar to you at all? Probably, because it's right there! But it's just a negative version of that. We need to throw in a negative. So, it's equal to the negative version of all of this good stuff right here. Okay, it's equal to the negative of that. No pirates quite yet, but it's equal to the negative of all that, okay? Which is pretty neat if you ask me. So anyway, then we've got this, right? We've got something really ridiculous right there. We've got the following, right? Negative mu times 1 over r cubed multiplied by the cross product of r cross h, which is just the right-hand side, right? And we just simplified this quite a bit, right? We simplified it to literally just this. It's literally just this. That's equal to negative mu multiplied by negative, as you can see there, derivative with respect to time of r over r is equal to negative derivative with respect to time. It's just a constant, so we can pull all of this stuff in. Oh, sorry, the negatives cancel out. Derivative with respect to time of mu r vector over r. Okay? Now, been a couple years, yeah, I know. This stuff all comes back to bite you in aerospace. It all comes back to bite you. So we've got time derivative of this with respect to r. So I now present to you, we've got two things, right? We've got the left-hand side of the equation, and then we've got the right-hand side of the equation. So let's go back to the original equation and let's see what it was originally before we did all of this nonsensical crap, right? Yeah, that's what I thought. Okay, cool. Sorry, I'm looking at my derivation. We've got the left-hand, we've got this. For whatever reason, we decided to cross Newton's gravitational law with angular momentum, for whatever reason. And then we looked at the left-hand side and the right-hand side of that equation. And then we took this left-hand side and we put it in terms of something, and then we took this right-hand side and we put it in terms of something else, all right? So let's copy first and foremost this equation down. So, right-hand side, well, let's put an equal sign. Negative mu over r cubed multiplied by r cross h. And again, this is just Newton's law of gravitation crossed with angular momentum. That's all this is. And then right here, this is just then r double dot crossed with h. We're crossing each side with h. If you took out these h's, then you just have Newton's law of gravitation, okay? And then we simplified it a little bit. We've got this left-hand side right here. I was about to point on the screen, but I guess you can't really see that. We put that in terms of this right here. So let's just take that down. D over dt of velocity crossed with angular momentum, right? So that's equal to d over dt of velocity crossed with angular momentum, and that's equal to the thing that we just solved for here. Oh. And the thing that we just solved for here, oh, crap, come on. I wish this thing didn't appear on screen every time I made a mistake. Euler momentum. Nice. Nice, YOLO. We've got this, right? Which is just equal to this right here. This is the right-hand side. is equal to d over dt of mu r over r. Beautiful. Absolutely beautiful. Check this out. No, I never messed that up. That was just one time that I messed it up. I don't know why. But guys, check this out. We've got a level playing field. Yes, this is still a time-dependent variable in here, but look, we're getting closer to a level playing field with everything at the same level of derivation. We're getting a lot closer, because now we've got d over dt and d over dt right here, right? And we can combine these now. We can do something really, really cool, and we can go like this. D over dt, all I'm going to do is move this side of the equation over here and combine the derivatives. So velocity vector crossed with angular momentum vector minus your gravitational parameter multiplied by the vector position over the magnitude of position, that's just equal to 0, okay? Because I'm just moving this over. Let's integrate, okay? Let's integrate a little bit and let's see what happens. So if we integrate, then we get this then. We get rid of this d over dt, r dot cross h minus mu r over r is equal to a constant vector. And I'm just going to put c there. It's a constant vector where c is a constant vector, right? Because when you integrate, you get a constant. It's a constant, but when you integrate with vectors, you get a constant vector. I did subtract the right side. You bet I did. Is a constant vector, okay? The video game industry standardized on left-handed. Yep, huge Unity left-handed, Unreal left-handed. Yep. I wonder if there's anything optimization-wise that happens in GPUs with left-handed coordinate systems. I have no idea. But C is a constant vector. Okay, so we've got this equation. C is known as the writing known as the Laplace vector. Okay. You guys ready for pointless move number 2? Hey Eric, what's up, man? How are you? Pointless move number 2. Pointless move number 2. Pointless move number 2. Numero dos. We are going to take the dot product of h to everything. Take dot product of the angular momentum vector to everything. Why? Don't worry about it. It's a pointless move. But this is going to show something really important, okay? So we're going to do it anyway. Get over it. We've got this then, right? Okay, so we're taking the dot product of h with everything. Why? Don't worry about it. Velocity crossed with angular momentum dotted with angular momentum vector minus the gravitational parameter multiplied by the dot product of r dot angular momentum over r is equal to your constant vector, your Laplace vector dot product with angular momentum. Okay? Euler's in what place? What? He's in Houston. He's not in Houston. What? He's dead. He's long dead. Alright, so check this out though. We can do some really cool things here, okay? We know, first and foremost, that that h, right? Remember h is equal to r cross v, right? Because of cross product mathematics, all these vectors are orthogonal, or v is orthogonal to h, right? So that means this will produce a vector that's orthogonal to h, which means that if you take the dot product of a vector to another vector that's orthogonal to that first vector, guess what? That's equal to 0. What about the same thing here, right? If you take r, which we know r is orthogonal to h, then taking the dot product of an orthogonal pair of vectors, that's equal to 0. So what does that mean? Therefore, c, your constant vector dot product with h, is equal to what? 0. What does that mean? Therefore, c is orthogonal to h. What does that mean in layman's terms? That means c, that Laplacian vector, is in the orbital plane. That's what that means. It's in the orbital plane. It's in the plane of the orbit. That's awesome, right? We've got something really powerful now, okay? We know that this random vector of integration that we came across happens to be in the orbital plane somewhere, because c.h is 0, and h is exactly perpendicular to the orbital plane, right? If this is your orbit right here, then h is, then h is popping right out of the orbit, perpendicular, which means that c is somewhere in the plane of the orbit, right? That's what that's telling you right there. So that's really cool. That's some really cool knowledge, okay? Here's what we're going to do. We're going to take this equation right up here. Before we did this little proof with the pointless move, we're going to take this equation right here, okay? We're going to copy it down. So the velocity vector, take the cross product of the velocity and the angular momentum vector, subtract gravitational parameter position vector over the magnitude of the position is equal to c, the Laplacian vector, okay? Here's what we're going to do. Yeah, it's elliptical. You bet, YOLO. It's an elliptical orbit. We're going to divide everything by mu. Divide by mu. Okay. Divide by mu. Why did I spell it out? Divide by mu. Okay, so then we're going to get this. Velocity crossed with angular momentum over mu minus position vector over r is equal to your Laplacian vector over mu. Does anybody know? Denial, like, told me know this. Oh! Oh! Beautiful, Kelly. Kelly got it. Yeah, he is. They were already used to modeling things left-handed, so they just kept it with it. Okay, that makes sense. Yeah, whatever. Whatever works. I don't mind working left-handed coordinate systems. I've done it enough now where I'm not going to complain about this. Anyway, does anybody know what this vector is? This vector divided by mu? Does anybody know what that is? It's actually a really common term that we typically use in orbit, and I'll give you a hint. It's called the eccentricity vector. This is the eccentricity vector. Boom. Surprise. You didn't know, but we were actually deriving eccentricity. Whoa! We've got eccentricity vector now. Whoa, whoa, whoa. Okay, we've got E. We've got eccentricity. Eccentricity. And we know that eccentricity is just the magnitude of the eccentricity vector. Okay? Whoa. Oh, wow, that was horrible. I got so excited about it. I got so excited about eccentricity that I spelled it wrong. It's the eccentricity vector. Eccentricity. Okay, it's the eccentricity vector. How cool is that? So we just derived the eccentricity vector. So now we know that eccentricity vector, is equal to V, which is just r dot, cross H over mu minus r over r. Check that out. If you've got position vector and if you've got velocity, you can come up with the eccentricity vector. And that's how you do it, right there. That's how you come up with it, okay? But we're not done yet, okay? We're not done yet at all. You want to know why we're not done yet? Well, is equal to r dot, right, which is just velocity, cross h over mu minus r over r. No, it's just a C for constant. C is short for constant. It was a constant vector, and that C vector is called the Laplace vector. But if you take the Laplace vector and divide it by your gravitational parameter, it'll give you your eccentricity vector. So anyway, here's the problem, right? Here's the problem. We still have this nasty time dependence. Nasty time dependence. Nasty time dependence. Nasty time dependence. Whoa, I don't want that, okay? Which... is this related to vis viva? It will be related to vis viva, in probably a later derivation. Honestly, man, at this point, I gotta be careful, because this is really like Aerospace 401, not Aerospace 101. But, this is related to vis viva. You can derive vis viva from all of these pointless moves that I'm making. Which, speaking of the devil, brings us to... pointless move number 3. The last and final pointless move of the night. Pointless move number 3. Pointless move numero trace. I don't know how these guys figured it all out. We're going to take the dot product of everything with the position vector. Come on now. With everything. Okay? Yeah, Kelly, you can derive energy just like that. Right? You absolutely can. RV.H. Where are you getting that from, Yellow Swagons? I don't think so. What's that M turn that... I don't know what this M turn is. Wait, what is M? I'm not sure, Yellow. I am not sure. You might be able to. I'm not quite sure what your notation is there, though. Anyway, we're going to take the dot product of everything with R. Why? Don't worry about it, okay? We've got this now. We've got eccentricity dotted with R is equal to the quantity of velocity crossed with angular momentum dotted with R over mu minus R dotted with R over R. Okay? Whoa! Yeah, Yellow, I don't think so. I think you must have messed up somewhere there, because you have now radius multiplying by velocity. You big bully! No, that was a real question, and it's actually true, Kelly. You can derive vis viva from this. You can derive orbital energy from this. Guys, hang in there. We're almost done this nasty derivation, okay? And we're taking everything. Let's move this over, right? So we have all positives, because I love positives. Who doesn't love positives, right? So R dot R, first of all, I'm going to go like this. Note, I should probably start doing this in a different color. Let's note this. Let's note this. I love positive bank counts too, yeah. Note though, right? Guys, I want you to try to simplify this for me. R dot R, R vector dot R vector over R. Simplify that for me. What is that equal to? That can be written in a much simpler way. And what is it? And I know you guys know it. No primes, Kelly. There's no primes. This is just R. There's no R dot or R prime here. It's just R. It's just position vector dotted with R. So no prime. You're close, man. You're close. You can make it simpler than that, though. You can make it simpler than that. Can none of you guys do none of you guys know what this is? Remember yeah, Novus. It's literally just R. That's all it is. Because really this is R squared over R, and that simplifies obviously to R. It's just R. That's all that is. So now we've got this, right? We've got R. Oh, and also we've got this, right? Oh, this is gonna be fun. Okay. We've also got this. Also, remember the rule, right? A dot B is actually equal to A, B, cosine of theta. Theta being the angle in between them, right? That's what it is. That's what it is. There you go. Nice, Novus. Yeah, I know, Kelly. It's all over the place. But that's what the dot product is. Hopefully you guys remember that from like geometry. It's A dot B is actually just, or trigonometry. It's just AB cosine theta. That's all it is. So we can do that with E dot R, right? So we've got this now. R plus E R cosine theta is equal to this nasty thing. V cross H dotted with R over mu. That was a bad line, sorry. Over mu. And then we're going to use another vector theorem. Use theorem. It was way too spaced out. Use this theorem right here. And the theorem is this. Vector A dotted with the cross product quantity of B cross C is actually just equal to the quantity of A cross B multiplied or dot producted with C. Or take the dot product of that quantity with C. Those are equal to each other. That's pretty complex, Kelly. We're not at that stage yet, okay? That's for Aerospace 501. Keep it simple, alright? Please keep it simple. Yeah, Kelly, that's a bit too much. I want this to be open to all audiences, so please don't overcomplicate things like that. All right, so now we've got this then, right? So and remember V right there, it's equal to R dot in that notation. So we've got this then. R dot cross angular momentum dot R is actually just equal to R dot vector dotted with what did I do here? R dot. Oh, I'm writing this on the wrong side, aren't I? Yeah. Wait, no, that's right. Well, it's confusing if I write it on that side. It doesn't make any sense if I write it on that side. So I'm gonna move this over to the other side, and it's just for visual purposes. It doesn't really matter, but so anyway, R dotted with R dot cross angular momentum is equal to R crossed with R dot dotted with angular momentum. Does anybody know what this R cross R dot is, by any chance? Does anybody know what R cross R dot is? I'll give you a hint. It's also R cross V. Is that familiar to any of you guys by any chance? Have you guys seen that before, maybe? King Crab, I'll go over that when I'm done doing the derivation, but I'll go over it. Basically, right? If you've got a vector A, and if you've got a vector B, then the dot product determines how similar they are to being the same vector, right? So if you've got A going out like this, King Crab, and if you've got B perpendicular, then A dot B in this case is actually 0. Okay. However, what the cross product is you take if you take, for example, B cross A. What you're doing is you're rotating one vector along the other vector, and you can imagine sort of if you're rotating B along A, then you're going to get a vector that's coming out of the plane like that, and that's the direction of rotation, and that is well, this is the right hand rule. And then you can imagine if you're rotating B into A, this is like the direction of rotation, and that vector is going to be B cross A. So that's the difference between them. Yeah, it's like multiplying in 3D space. Yep. It's not A. R cross V is just H. But note, right? So note, R cross R dot is equal to R cross V, and that's just angular momentum, right? R cross V is just angular momentum. Which means that we've got this then. We've got this. R dotted with R dot cross H is really just equal to H dot H, or H squared. Beautiful, right? Now, where did this even come into play? Explain the cross again. I'll be able to explain it better. Oh, Kelly, yeah, I know. It's fine, man. But H dot H, it's just H squared. Yeah, make guesses, guys. So where does this come into play again? This thing right here. This is this right here. So we're just taking this, and we're solving for it down here. So now we've got this ridiculous thing, and we also have a mu, right? So we've got a mu divided by mu, divided by mu, and divided by mu. So now we've got this, all right? R plus ER cosine theta is equal to H squared over mu. Guys, do you see a single time derivative in there? Do you see a single time derivative in there? No. We put everything on the same playing field. There is no time derivatives in there. There's no derivative of an object. There's nothing. we put everything on the same exact playing field. So let's simplify a little bit. Okay, so we've got r, and we can take this out, right? We can take r out on this side. 1 plus e cosine of theta is equal to h squared over mu. Now, let's solve for r. It's all Euler's on the field. Yeah, you bet. R, therefore, big therefore, your position, your magnitude of position, r is equal to h squared over mu over 1 plus e cosine of theta. This equation right here, they call this the orbit equation. That's what this orbit equation is called, okay? Orbit equation. It's called the orbit equation. We just derived literally the orbit equation, okay? Now, if you guys remember, like this theta, remember, so let me just go like this. Remember, theta is the value, is the angle in between what two vectors? It's the angle in between the eccentricity vector, which we know is in plane. We proved that the eccentricity vector is in the orbital plane, and r, okay? Now, it just so happens to be that when you have an orbit, and let me draw an orbit here. When you have an orbit, and let's say the orbit looks something super fancy and smooth like that. Let's say you have an orbit. This is your planet. This right here is called the apse line. Okay, we call this the apse line. Come on, apse line all the way through, please. It's not really a line, like an apse squiggly. Anyway, this right here is what? This is the direction of what's called the radius of periapsis, right? Because this points towards the periapse point. Periapsis. This is the apoapsis, right? Apoapsis. Apo for far. Apoapsis. This is called the apse line. Right here. This is the apse line. Bigger theta. Oh, the theta's fine. The theta's fine. But anyway, this is where the eccentricity vector lies, right? This is eccentricity. That's the location of eccentricity right there. It points along periapsis. So I'm gonna write that down. Eccentricity points along periapsis. Whoa, and that's always the case, okay? I'm going to start this because this is going to be a worksheet number 2, so just keep that in mind. Eccentricity points along periapsis, okay? Now check this out. Again, theta is the angle in between E and R. So let's say that our object is right here, okay? And let's say you're orbiting the object. Well, I just mucked all of that up. You're orbiting the object, right? You're orbiting your planet. Okay, I'm really just doing something fancy here. This is your position vector, and I know it's a horrible line, so sorry. This is your position vector. This is R, okay? Hey, Bougie, what's up? Bougie, you came here for the grand finale, by the way. Which means that theta, again, is the angle in between the eccentricity vector, which is a constant. We determined it was a constant, and R. We call this theta. We call theta true anomaly. And whoop-de-doo, folks, true anomaly is our 6th element. That is our 6th element. Equals 6th element. And it changes. And it changes. Right? It changes over time. And it changes over time. Ladies and gentlemen, we have our 6th element. True anomaly. The angle in between this vector that we determined was a constant and the position vector. So guess what? We've got 6 elements now. We've got... What are our 6 elements? We've got semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of periapsis, and true anomaly. Okay? Oh, it did, King Crab. Guys, our worksheets after the class. I'm gonna go over worksheet number 1 in just a second. These right here are constant. They don't change in the two-body problem. This guy changes. Okay? That guy changes. D theta dt. Yeah, change in true anomaly. Guys, we've got 6 now. This is our number 6. Boom. Now, a few things to keep in mind, alright? So I'm going to write down a few notes here, okay? A few notes about this. You don't need to use these 6 elements. You don't need to use these 6. You can use any 6 that makes sense to use. These 6 elements. It's not necessary to use these 6, okay? There's other sets of orbital elements that you can use. This is just a set that you can use, and it's a common set, okay? Typically, what happens... oh, okay, I don't know what that was. Typically, there's 5 constant ones, right? So there's 5 constant, like the ones that I've just shown you. And then there's 1 time-dependent one, right? Are these elements derived from a single equation? No. No. No, multiple equations. Take a look, King Crab, at the last AERO 101 lecture, and you can see how we derived AEI, omega, and omega. Exactly, Bougie. That's exactly what happens. And again, as I mentioned, right, you've got the problem you're trying to deal with is we don't know where we are along the orbit, but the first 5 elements specify the orbit, and the 6th one tells you where you are along the orbit, okay? Now, here's the thing, right? That 6th element could be things like, 6th element could also be, 6th element could also be, for example, it could be this. It could be time at periapsis. Time at periapsis. What time did you cross the periapsis point? It could be time at apoapsis. Time at apoapsis. It doesn't really matter. But your 6th term needs some time dependence to tell you either where you are currently or where you were at a specific time. Okay? You got that? So now we have this. So we've got... So really, theta, true anomaly, is actually a function of time. It's really a function of time. And it changes over time, obviously. So again, we've got this. R is equal to h squared over mu over 1 plus e cosine theta. And to make it a little bit simple, note from last time we derived semi-lattice rectum. Time since you put the turkey in the fryer. That is an excellent 6th orbital element. Time since, well, sorry, I got a little bit confused there. We derived semi-lattice rectum, semi-lattice rectum to be p is equal to h squared over mu. We derived that last time, okay? We already know that. Oh, Kyran, that is beautiful. That is a beautiful sentence right there. Yeah, King Crab. This is rectum as in rectangle, like rectangle. Come on, keep it classy. So we've got this then. R is equal to P over 1 plus E cosine theta. Okay? Check this out. What happens Oh, and note P is also equal to A1 minus E squared. Okay. Nice, Kyran. So we're not gonna do too much with this equation. We're gonna mess around with this equation a lot next time. But for now, I think I'm good with just this, right? So we've got R is equal to P over 1 plus E cosine theta. So check this out. For any true anomaly, if you know H and mu, if you know your eccentricity, and if you know, wow, that is like really small, isn't it? Let me bump it up in size a bit. So, what do we know then? If you know eccentricity, if you know it's your semulatus rectum, then check this out. You can plug in any value that you want. So again, if your orbit looks like this, you can plug in, and this is your eccentricity vector. Let's say you're right here, right? This is your radius vector. You can plug in any value you want for theta right there, and it will tell you the magnitude of your position vector. How cool is that? This equation is literally, you plug in any angle along the orbit that you want, and it will tell you how far away you are in that orbit. It's that easy. And you can do the same thing backwards, right? You can solve for theta, and you can basically say, all right, at this position vector, what is my true anomaly? I know I'm this far away, but what's my true anomaly? Okay? It does kind of look like Winnie the Pooh. It definitely does. Oh, that stinks, Kyran. Anyway, this is awesome, right? And that's why theta is a good choice. Because look at this. For any value of theta, we can get position vector r using one equation, the orbit equation. How awesome is that? There's an equation called the orbit equation. The orbit equation. Boom. Bada bing, bada boom, the orbit equation. We did it, guys. Orbit equation. It didn't really take us too long. It took us a lot of work, though. It took a lot of work to get there. Like, a lot of work to get there. A lot of work to get there. That's why theta is a good choice. And this is what we came up with. The orbit equation. H squared of mu over 1 plus E cosine theta. Boom. Alright. We have the orbit equation. Alright, so I'll tell you what, guys. This was awesome. We got our sixth element down. I'm going to go over the worksheet. That I came up with. I will show you guys the problems. So let me get set up here. Again, worksheet is not required by any means, but I'll tell you what. If you do, even if you only want to try like one problem on the worksheet, go ahead and try it, and your reward for trying it is that I will look at your work, and I will in-depth tell you what you did wrong, and where you went wrong, and maybe we'll go over it on stream and make fun of you for it. But that's only if you're lucky. Alright, so let's look at this, no, we're not going to make fun of you for it, obviously. We are going to, Let me get the note packet here, wherever I put this thing. I think I put it on the drive. I believe I put it on the drive. I hope I put it on the drive. Oh, Demonata, I just got your message, man. Good stuff. Good stuff. That's awesome. And I'm glad it was an improvement too. Make more fun of me. No. Oh yeah, good reward. I know. Alright, so let's go to the drive and let's take a look at this problem set here. But seriously, guys, I'm not telling you to do it, but I really want you guys to at least give these a try, okay? It won't take a lot of time. Everything that's in this problem set is also in the note packet, okay? And it's really not that difficult, and it'll keep you fresh on this stuff. Guys, I can't stress this enough. Yeah, I'm like the back of the textbook. Guys, I can't stress this enough. Understanding space, understanding orbital mechanics, that's what the universe is. That's what the cosmos is. That's what we have come to know and understand in our life. Okay? Understanding this is understanding yourself. Understanding this stuff is understanding how space operates, like how space works. I'm telling you, it doesn't even matter if you're really in the field or not. Understanding this stuff is really cool because, again, you're understanding yourself. You're understanding how space and time work, okay? And that's awesome. Anyway, Let's take a look at the problem set, shall we? Let me stop complaining here. Well, I'm not complaining. I'm ranting. But that's what it is, right? That's what all of this stuff is. It's important. It's really important. It's very, very important. All right, let's take a look at the problem set here. No, just give me the answers. Let's take a look at the problem set here, okay? I mentioned which lectures you should reference, right, when you're working on this problem set. I mentioned, again, don't fret over it if you don't understand anything. Skip anything you want to. That's totally fine. Send me it when you're done, and I'll go over the problems, and I'll see what you're doing right, what you're doing wrong, and I'll help you. That's the whole point. I'm going to help you. I'm going to help you understand this stuff. You're understanding space and time. You're understanding yourself. If you're handwriting the problem, again, just keep it legible, right? Make sure to, like, I can read it. That would be a little bit easier for me, obviously. All right, first things first. I go into names, symbols, and acronyms, okay? So I've got either, right, a name, so I'll have a quote on here. This is something somebody said, and let's take a look at what it says. We inherently know all ideal forms of all objects. There's no due date, Demonata, no due date. Just do it whenever you're ready. We know all ideal forms of all objects, and our senses simply allow us to see recollections of these objects. We inherently already know everything. Who said that? AERO, what does that stand for? God is perfect and created perfect circular orbits. Also, the Earth is the center of everything. Who said that? You get the idea. Argument of periapsis. What is the symbol that's commonly used for that? You keep going. What does GCRS stand for? Who said this? Who said... Oh, I can. Group test 1 is Plato. You got it. 1 was Plato. You got it. Yeah, I can't read chicken scratch. 1 is Plato. You absolutely got it. Yeah, if you guys know the answer to any of these, feel free to shout them out. That's totally fine. But 1 is Plato. Plato thought that we inherently already knew everything. That's what Plato thought. And here's another one. Somebody used Tycho Brahe's observations to determine an orbital mechanics model consisting of 3 laws. Okay? Number 4. How are you already numbering? 1, 2, 3, 4. Argument of periapsis. Well, if it's easy, that's good. That means you know what argument of periapsis is. That's good. And then, like, what's the Newton Principia? You got it. Author of Principia Mathematica Philosophica Naturalis was Newton. That was absolutely Newton. What does this symbol stand for? You know, I'm not going to tell you, but what does that symbol stand for? What does STEM stand for? You guys should all know what STEM stands for. Who said this? Who said that Plato was wrong? Oh, it's fine, Demonata. It's fine. You can also just type up your answers. That's fine, too. Plato was wrong. We develop ideal forms over time, right? We develop ideal forms over time. Notice. Tommy, are you saying this one is King Crab? Are you saying this one is King Crab right here? Because if you're saying that, then you're actually wrong. We develop these ideal forms over time using our senses. We don't know anything at birth. That's the difference. And then what's the symbol for gravitational parameter, and what does ITRF stand for? Probably the ones that you guys are going to have to read through the notes for are ITRF, GCRS, and IERS. To learn what those stand for. No, the other one? Which one? The God is Perfect one or Tycho Brahe's observations one? It doesn't matter. You got it. All right, next section, right? Postulates and laws. Write in your own words. I don't care how you do it. Hopefully you don't just copy it off. What are Newton's 3 laws in order, and what are Kepler's 3 laws in order? And then this is cool. I've got a go no go section. Okay, it's a true or false. It's a true or false section, but I like to call it go no go. I think that's kind of cool. No tenures, man. No tenures. This is a not-for-profit. I'm a not-for-profit professor. I do this out of the will of my heart because I want you guys to understand this stuff. I want you guys to understand and know this stuff. I've got a go-no-go section here. All right. So Newton's law of gravitation breaks down on galactic scales and may be only an approximation to the true model of gravitation. And all you have to do is write go or no go. Go for true, no go for false. Okay. Would I consider a tenure? I don't know. I haven't really thought about teaching. I want to spend time in the industry before I go back to academia, I think. Nope, no editable boxes. I'm not that good, man. I'm not that good. How about this? You can use Newton laws in any frame, inertial or non-inertial, go or no go. The ICRS is not a perfect inertial frame, go or no go. Hyperbolic orbits are characterized by negative semi-major axes, go or no go. Alright, all you gotta do is write go for true and no go for false on these. Next page. So, now we're gonna get into some of the problems, okay? There's two problems, okay? There's problem 1 and there's problem 2. There's two main problems here. And these are the mathematics problems. And I'll show you what these are. You can use any equation derived in the notes, as I mentioned, right? If you have to look something up online, though, you're probably doing it wrong, right? That probably means that you're doing something that you probably shouldn't do, okay? Hey, Sonny, what's up? So anyway, here, I mentioned here, again, any equation that you would need, you can just pull it directly from... you can pull those equations directly from... What am I saying? Sorry, I lost my train of thought. You can pull those equations directly from my notes, and you're not going to have to look up anything online. So, and I give you some constants that might help you out a little bit. I give you Earth's gravitational equation, right? Vis via? Where do I say vis via? Oh, crap, it's vis viva. That's actually not the only typo, guys. Not even gonna try? Why not, Sonny? That kind of makes me sad. That kind of makes me sad that you won't even try it. But anyway, whatever. I guess if you don't want to try it, that's fine. I'm gonna be sad about it, but alright. Vis visa? Yeah, there's multiple typos on the page, guys. This isn't professional, okay? It's something I want it to look professional, so I'll obviously fix the typo. This is not the only typo, okay? I saw another typo and I left it in there, so that's for you guys to figure out. Okay, so let's read problem 1, okay? Nice, Kyron. So, you just started a new position, okay? Like way above. Alright, man. I mean, it's in the notes. Again, it's in the notes if you want to look at the notes, but that's fine. I get it. Some of this math is a little bit above people, and that's fine. But don't limit yourself, right? Don't limit yourself. It's only above you because you haven't learned it yet. It doesn't mean you can't learn it yet. Too many omegas. Guys, good news, by the way, great news, you got hired, okay? You got hired. You're working at a new stellar observatory. Congratulations on your new position. You're tracked to characterize, your supervisor comes up to you the first day, he's like, boom, I got 2 objects that I want you to track that are in Earth orbit, that just appeared in Earth orbit, and we want to track them, okay? And right now, it liquefies your brain. That's kind of good. Demonata, again, man, I already told you Demonata as well. Dude, I want to help. I want to help you guys understand this stuff, so come with questions. I know that I can't teach you calculus over Discord, but, you know, come with questions in the Discord, and ask questions in the AERO 101 channel in the Discord, okay? How much does it pay? Well, it pays nothing if you get the problem wrong. So, your supervisor basically says this. I have 2 objects that I want you to track. I want you to track this new object that we're calling alpha and this object that we're tracking omega. And he gives you some information, okay? He basically says this. He says object alpha, he gives you the altitude of object alpha, okay? He gives you the altitude of object alpha, and he gives you the velocity of alpha. He gives you the altitude and velocity of alpha. And then he gives you some information about omega, and actually the only thing he gives you about omega is the orbital semi-major axis. So for one case, you've got the altitude and you've got the velocity, in the other case, you've got the semi-major axis, okay? First question here. Any alphabet similar directory you want, no need to limit the boring. Yeah, no need to limit. Hey HVAC, how are you? But first question I'm asking, what are the orbital energies, right? And guess what? You can use the vis-via equation, or the vis-viva, more commonly known, right here. And which orbit, I ask, has the higher or the less negative energy? Which orbit has more energy? And then I ask you, what's the semi-major axis of object alpha? Because check this out, you've got altitude of alpha, and you've got velocity of alpha, but you don't have semi-major axis, okay? Oh, that would have been cool, man. So anyway, I give you a hint here, right? I say use the vis-viva equation, the vis-via equation, V squared over 2 minus mu over r is equal to negative mu over 2a. That's equal to your energy, right? Those are all equal to each other. V is velocity. Oh, what? This one, bougie. The information in here is actually from the previous lecture, man. The information for this problem has nothing to do with what we just derived. Nothing on this worksheet has to do anything with what we just derived. The things that we just derived for the 6th element is not going to be on here. Not on this worksheet. But I ask you then, right? So we check this out. For example, I'll give you a little hint, right? And use the following assumption. I give you the radius of the Earth and you have the altitude. So if you add those together, you get position, right? You get r. So in that case, we're object alpha. We've got the altitude and we've got velocity. Because we have altitude and because we're orbiting the Earth, we know, position. So we've got v squared and we've got r and we know mu. We know mu of the Earth, so we can calculate E, okay? There you go. The 5th element. Oh, I don't care. I have no preference. So that's how we calculate the E for the 1. How about for the other one, right? We only are given the semi-major axis, right? Yeah, bougie. We only need semi-major axis here, right? Well, check this out. We can actually just calculate energy from semi-major axis. So that's how you calculate the energy of the two. And I'm not going to go any further, right? That's how you calculate the energy of the two. Moving on to the next problem. I give you a work page just in case you're doing this by hand. You don't want another piece of paper. All right, next problem. Upon doing more research into a 3rd object. Now we're looking at beta. I know beta is the 3rd object, but whatever. It's meant to confuse you. And this is not something your supervisor gave you. This is something that you want to do this by yourself, okay? Well, it's not going to plow into Earth if you figure out the energy and figure out a way to save it. But we've got a 3rd object of beta, and this is not something your supervisor gave you. This is just something that you want to bring to your supervisor. Be like, ha, guess what? I determined the orbit here. And you only know, to start, the angular momentum vector. We've got the angular momentum vector expressed in kilometers squared per second. That's the angular momentum vector. And I ask you, first and foremost, what's the magnitude of the angular momentum vector of beta's orbit? And this, all you have to do, sounds good, bougie. All you have to do is take the magnitude of this vector. And if you don't know how to do that, again, you can look that one up online, because I don't provide that, the magnitude of a vector. And then I ask you, what is the orbital inclination? What is the orbital inclination? Well, I'll tell you what. There's an equation for orbital inclination that I don't give you, and you're going to have to find in the notes. Use the trigonometric equation for inclination, as well as all the equations in the semi-major axis calculation portion of the orbital element's notes, okay? I hope not, Kyran. And these are some helpful equations that you can use, okay? But anyway, I go like this. I give you that. So what's the orbital inclination? And then I ask you, what is the semilatus rectum of the orbit? Well, I'll give you a hint. Semilatus rectum is equal to h squared over mu, so you can calculate that. And then I say this. Let's say then you find out beta is orbiting with an eccentricity of 0.2. And with that eccentricity, you can calculate a lot of different things, like semi-major axis, A, radius of periapsis, and radius of apoapsis. So this problem is really just determining a bunch of different characterization parameters of this orbit. Oh, it's fine, Kyran, I don't care. Anyway, 711 Space Program. Okay, so this is just, characterizing things about the orbit now. So those are your two problems. You've got a main problem here, and you've got a main problem here. You've got two main problems, and before that, there's some true, false, there's some other things, and then there's fill in the blanks. Guys, keep in mind, I am not going to be offended if you decide that you don't give a crap about this stuff. I want you guys to try to fill some of it out, and I want to see you guys, try at least some of it. Even if you don't see the problems, just fill out the, intro material. I want to see you guys try at least some of these. And if you can't get it, then it's fine. I understand. If you don't have time, trust me, I understand there. Time is everything, and time is really hard to come by sometimes, and I understand that entirely. So if you can't get around to doing it, it's no problem at all. I'm not going to blame you or anything for it, right? It's fine. But how do we submit? I don't know. You can take a picture of it if you want. You can scan it in. Yeah, yeah, exactly, Kyran, like, I'm not gonna ask you to do it in the kind of week that you just had. But, see, just try it. Just try it, that's all I'm asking. And I'm telling you, if not a single person submits it back, I'm not gonna be offended, I don't care. I'm still gonna keep doing this, though. Even if not a single person puts information out there, I'm gonna keep doing it. I'm always going to keep doing it, okay? Because this is kind of what I care about. I care about spreading information like this. So I'm going to keep doing it even if nobody submits anything. That's totally fine. This is available on the Google Drive, so you can use... what can you use? You can use that AERO 101 command to find out information for it. Okay? Yep. Just go to the Drive, Kyran. Right there. Yep, Kelly's got it. Yeah. Just go to the Drive. Go ahead and try them. All right. You might find out that you know more than you think. All right. And here's the other thing: if for whatever reason you guys do decide to do this and come back and you say these are too easy, well then I'll give you more challenging problems. I guarantee I'll give you more challenging problems. All right. Anyway, go ahead and try some of these, all right? That might be a bit fun. Again, understanding space is understanding yourself. Understanding space and understanding the things around you, well, that's what you're made out of, right? We're all made out of star stuff, all right? Well, there you go, HVAC, exactly. Yeah, man, I'm not copying this stuff from the textbook. I derived the orbit equation myself. I just did this before the stream. I derived the orbit equation myself. So you're not gonna find this exact derivation anywhere in any textbook. This was my representation of it. And again, I have to simplify some things. I have to simplify a lot of things, but I don't know. I think that's part of it. Guys, go ahead and try this out. You might find it to be refreshing to learn a little bit about how orbital mechanics actually work beside Kerbal Space Program, right? You might find it refreshing. So go ahead and try this set out. Bougie, you're the most star stuff. You know that, man? You're the most star stuff. Well, Demonata, I know. Chromodynamics with me? I know nothing about quantum chromodynamics, man. I know absolutely nothing about that. Kyran, where's that astronomy stream, man? Where's that astronomy stream? Guys, if you want more information about people like me that go out and try to teach other people things like you, I have a link for you that I want you to go to, that I'm requiring you to go to, that I'm forcing you to go to. And let me pull it up real quick. The link is as follows. The link is right here. Go to that Discord link. Check out Twitch EDU. All right, it's a group of people that love doing this kind of thing. I love doing it too, obviously. But anyway, I'm gonna switch gears here. Switch gears and drink beers. Drink beers and switch gears. Do it, Bougie. Do it. And Bougie, if you want, again, go into that Discord, Bougie, if you have Discord, and just pop into the main text channel and just say, hey. Be like, hey, just letting you know, I'm another guy that does Twitch EDU streams, or that wants to do Twitch EDU streams. Bougie, it's another way to meet people that are interested in this stuff. Just hop in that Discord and basically say, hey, I'm an Arduino master, and I plan to do some of this stuff, you know? I don't know. Kyran, I've got off Friday. Friday's a government holiday. But anyway, go ahead and try that worksheet, guys, and check out Twitch EDU. Two things that I want you to do. And I'm going to switch gears here. Hey. What's up, Kelly? How are you? I'm going to switch gears. Well, Bougie, you're pretty good, man. You know way more than I do. I'll tell you that. I'm already tearing through this Wacom tablet. You guys see those scratch marks on it? That's not grease or oil. That's scratch marks. It's funny because you can tell where I typically write on the tablet. Play Breaking Benjamin. Okay, I might. I'm gonna cut the stream here. I might cut the stream here just so I can export this as a video. Yeah, I gotta find a protective film. I know. Probably help. Wacom tablet. Yep. Now, I mean, this is a good pen, King Crab. It's the pen that came with the set, so it doesn't really get any better than that. It's the pen that came with the set, so not really much that I can do about that. Oh, really, HVAC? That's cool, man. I don't know, King Crab. I don't know, man. Yeah, it's something that I have to figure out. I know. I just haven't figured it out yet. It probably will. Yeah, I think a screen protector is the best way to go about it. Let me go into KSP here. Actually, what time is it? I've been getting crap sleep because I've been streaming so often. Now that I think about it, let me just check something real quick. Thank you for the patience. It's 22:38. Okay. At a dollar store? But I would want to make sure it's a good one, right? I don't know. Alright guys, well I think I'm actually done. I've had a long day. I want to go on. I'm going to pass it over to somebody that is also part of Twitch EDU that you guys probably know of. His name is EJ. So, hey, welcome aboard. So, disposable ones? I don't know, it doesn't matter. Anyway, guys, you can hang out in the chat for a little bit. I'll be hanging out in the chat cleaning some stuff up, but I'm going to pass the ball over, pass the torch over. So, guys, I will see you later. Thanks for hanging out. Thanks for AERO 101 Lecture 3. It was a success, and I had a lot of fun. So, thank you for hanging out. I'll see you guys later.